Okay, so we're asked to answer the following for these systems of equations. The first question is if the system is consistent, and the second question is how many solutions does the system have? So go ahead, pause this video if you know what these questions mean and you think you can do them, and try solving them on your own. Otherwise, let's go ahead and try solving these questions.
Before I get into this video, you should know that this is actually a segment of a larger free video series called the Ultimate Linear Algebra Guide, where I go into each concept more in depth alongside problems and solutions linked to each video. So go ahead and check the description to see if the corresponding Ultimate Linear Algebra Guide video has released for this concept, and if it has, go ahead and watch that video. But those videos do take a while to make since they're much longer, so if that video hasn't released yet, you're welcome to stick around and watch this video and then wait for that video to release. Go ahead and subscribe to my channel as well so you'll be notified when the Ultimate Linear Algebra Guide has released if that's something you're interested in. And now let's get back into the video.
So for the first system of equations, we see that this is a homogeneous system of equations. So a homogeneous system of equations is basically when the system's constant terms are all zero. So all the terms that these equations are equal to, or their constant terms, are equal to zero. So that essentially means that the system is homogeneous, and every single homogeneous system of equations is consistent. So the answer to the first question is yes. So a system of equations is consistent when essentially there is either one solution or infinite solutions. In other words, a system is consistent when there's at least one solution. So every single system of homogeneous linear equations is consistent. And once again, a system is homogeneous when all of its constant terms are equal to zero, as we see here. Now, the next question is, how many solutions does this system have? So once again, a homogeneous system either has one solution or infinite solutions. It's either one of the two. The reason that a homogeneous system can never have no solutions is because every single homogeneous system of equations can be solved with the trivial solution. So the trivial solution is essentially when each variable in this system of equations is equal to zero. So x1 would equal 0, x2 would equal 0, x3 equals 0, and x4 equals 0. If we have that all variables equal 0, we'd get the two equations to be true, hence it's a solution to this system of equations. And it's pretty clear to see that it would also be a solution for every single homogeneous system of equations that exists. And the reason for that is 0 multiplied by any constant is 0, and if you add zeros, you still get a zero term. So the 0 is a solution for every variable, and we end up calling this the trivial solution. So since a trivial solution can satisfy every single homogeneous system of linear equations, then we can say that no system of homogeneous linear equations can have no solution. Now, how many solutions does this system of equation have? So here, when we do this, whenever you're asked how many solutions a system of homogeneous linear equations has, write out the number of variables and number of equations. Here we have 4 variables, and we have 2 equations. Now, the reason that this is important is because if we have more variables than equations in a system of homogeneous linear equations, then essentially we will always have infinite solutions. I'll repeat that because that's very important. If you have more variables than equations in a homogeneous system of linear equations, you will always have infinite solutions. So the answer to this question is infinite. To summarize, a homogeneous system of linear equations is when every single constant term in the system is zero. Or in other words, if you rearrange the system of equations to have all of the variables on one side and the constant on the other side, all of the equations would equal 0. Every single homogeneous system of equations has at least one solution. Or in other words, it's consistent. So since this is a homogeneous system of equations, it is consistent. Since this homogeneous system of equations has more variables than equations, then it has infinite solutions. And every single homogeneous system of equations can be satisfied with the trivial solution, which is when every single variable in the system is equal to 0. Okay, so those are the key facts of homogeneous system of equations that you should remember. And now I'm going to move on to systems that aren't homogeneous, namely these two systems here. So this system isn't homogeneous because here we can see that the constant terms in the equations aren't equal to 0. So whenever we have a system that isn't homogeneous, we need to find its row-reduced echelon form in order to determine whether it's consistent and the number of solutions that it has. Now, in previous videos, we actually procedurally found the row-reduced echelon form using Gauss-Jordan elimination, but here, from this video onwards, I'm just going to use my calculator to do so because I expect you to know Gauss-Jordan elimination at this point, and also because in most linear algebra classes at this point of the course, you'll probably have a calculator anyways, so you don't usually have to do Gauss-Jordan elimination. However, if you don't feel comfortable with Gauss-Jordan elimination, I highly encourage you to pause this video, go back, watch my previous video on Gauss-Jordan elimination, come back here, and then try doing this system on your own without the use of a calculator. Okay, so let's go ahead and first create a matrix that represents this system of equations. So the first column would have the coefficients of x1, so 1 and 2. The second column would have the coefficients of x2, so 1 and 3. The third column would have the coefficients of x3, so 3 and 5. And the fourth column, which we add on, or augment is the technical word for it, would be 4 and 7, or the constant terms. Since the constant terms aren't equal to 0, this system of equations isn't homogeneous. Now, we can use this matrix to find the row-reduced echelon form and determine whether the system is consistent, or in other words, has at least one solution, and how many solutions the system has. So let's go ahead and do that and find the row-reduced echelon form of this matrix. So I just plug this into my calculator, and I can show that we are finding RREF by writing RREF and drawing an arrow over it. And once I do that, I get the following matrix. Okay. Another thing is that this matrix is technically called the augmented matrix, this one right here, of this system of equations because we added on or augmented a column that contains the constant terms to the coefficient matrix. So here, this is the row-reduced echelon form of this matrix. The first column represents x1, the second column represents x2, the third column represents x3. To determine whether this system has infinite solutions or no solutions, we can go ahead and go down the columns of each variable and see whether it has a leading one or not. So the column for x1 has a leading one, because this is the first non-zero term in this row. The column for x2 has a leading one, because this one is the first non-zero term in this row, but the column for x3 doesn't have a leading one. So this is a leading one right here, this is a leading one right here, but this column doesn't have a leading one. Since the column doesn't have a leading one, and we don't have an impossible equation like 0 is equal to 4, this system of equations has infinite solutions. In other words, the system is consistent and it has infinite solutions. If, for example, let's say that the column x3 did have a leading one, then this system of equations would have one solution. And if we had an impossible equation like 0 is equal to 3, then this system of equations would have no solutions and it wouldn't be consistent. Once again, a system of equations is consistent when it either has one solution or infinite solutions. That's very important. That's why I'm repeating it so many times. Now, let's go ahead and let's move on to this last system of equations. Actually, before we do so, I want to say one more thing about this system of equations. Here, we once again have more variables than equations. So we have three variables and two equations. Now, the reason that this is important is because whenever we have more variables than equations, we either have infinite solutions or no solutions. Since here we didn't have a column with the leading one and don't have an impossible equation, this is an example of the case of infinite solutions. This system right here, which also happened to be homogeneous, is also an example of a case with infinite solutions. A homogeneous system of equations that has more solutions, more variables than equations, is always going to have infinite solutions because the case of no solutions is impossible for a homogeneous system. But here, the system of equations has infinite solutions as well, but it could also have no solutions because it's not a homogeneous system. Okay, now moving on to this last system of equations. Here we have three equations and two variables. So we can't really tell whether the system has no solutions, infinite solutions, or one solution, but we're going to find out. Okay, so let's go ahead and let's create a matrix for this. Since this is an homogeneous system, we can't really tell anything from directly looking at it, so we have to create a matrix in order to find out more. So let's do that. The first column would represent x1, so 1, 2, 2. The second column would represent x2, so the coefficients of that would be 2, 1, 4. And the third column, which we augment or add on, would have the constant terms, so 4, 5, and 8. Now, we have to find the row-reduced echelon form of this matrix in order to tell whether it's consistent and how many solutions it has. So let's go ahead and do that. The row-reduced echelon form of this matrix is going to be this. Once again, I'm just using a calculator to do this because usually at this point of the course, you will be allowed a calculator, but you do want to know the procedure. And if you need to find out the procedure, you can go ahead and watch my previous videos on Gauss-Jordan elimination, come back here and try practicing with this matrix. Okay. So this is the row-reduced echelon form of this matrix. Now to find out the number of solutions it has, and hence whether it's consistent or not, we can go down each column and see if they have a leading one. So x1 has a leading one right here, and x2 has a leading one right here. Since both columns have leading ones, and we don't have an impossible equation, like 0 is equal to 3, then this system of equations is consistent because it has one solution. If a column didn't have a leading one, then this system of equations would have infinite solutions. And if this system of equations had an impossible equation, like 0 is equal to 4, then this system of equations would have no solutions. So is this system consistent? Yes. How many solutions? 1. Because each column had a leading one, and we didn't have an impossible equation. So to summarize, let's go back through all of these problems and just summarize exactly what I did. A system of equations is homogeneous when all the constant terms in the system are equal to 0, like right here. Every single homogeneous system is consistent, which means that it either has one solution or infinite solutions. In other words, it has at least one solution. If a homogeneous system of equations has more variables than equations, then it has infinite solutions. Every single homogeneous system could be solved using the trivial solution, which is that every single variable equals 0. If a system of equations isn't homogeneous, to find out the number of solutions and whether the system is consistent or not, we need to make the matrix into row-reduced echelon form. Once we do this, we can check whether every single column has a leading one, and if the row-reduced echelon form has any impossible equations, such as 0 is equal to 4. If the row-reduced echelon form doesn't have a leading one in a column and doesn't have an impossible equation, then that means it has infinite solutions. If every single column has a leading one and there's no impossible equations, then that matrix has one solution. If there is an impossible equation, such as 0 is equal to 4, that means the matrix has no solutions. You can see that I showed you that in both examples.
So that's the video. On screen, you should see a link to one of my other videos and a playlist that contains every single individual linear algebra video that I've made so far, in case you want help with any other concepts that I've covered. In the comments, you could leave any questions that you have about a concept that I covered in this video, or if you caught any errors, you're welcome to leave one of those there as well. And I will see you in the next one. Until then, I hope that this video has taught you just a little bit more about homogeneous systems of linear equations and how to find whether a system is consistent or not. See you next time. Bye!